Quantum mechanical harmonic oscillator. The Schrödinger equation for the quantum mechanical harmonic oscillator may be written as minus h bar square over 2m psi double prime plus 1 over 2 m omega square x square. Psi is energy times psi, where omega is square root k prime over m is the angular frequency for classical oscillations. Its solutions may be cleverly addressed using the following observations. The difference in applying two operations A and B in opposite order, called a commutator, is denoted by square brackets A and B is AB minus BA. For example, if A represents differentiation so that A applied to f is df dx, where f is a function of x, and B represents multiplication by x, then AB commutator is d dx x commutator, which is d dx applied to x times f minus x times df dx. Applying the product rule for differentiation on the first term, we determine d dx x commutator applied to f is f, which we summarize by writing d dx x commutator is equal to 1. So if you take a derivative with respect to x, you will get x times f plus 1 times df dx plus x times, so we're going to get 1 times f plus x times df dx. So this is minus x times df dx. They will cancel out and we will get f as it's suggested here. Similarly, consider the two operators a plus and a minus, defined by a plus or minus is equal to 1 over square root 2 mh bar omega minus or plus h bar d dx plus m omega x. So part A, determine the commutator a minus a plus. And part B, compute a plus a minus applied to psi in terms of psi and the second derivative psi double prime, where psi is a function of x, it's a wave function. Be mindful that d dx x psi is psi plus x times psi prime. And part C, the Schrödinger equation above may be written as Hamiltonian operator applied to psi's energy times psi, where h is a differential operator. Use your previous result to write h in terms of a plus and a minus. So this is what I will do in this video. So first we will start with determining the commutator. Let's rewrite our a plus a minus operators. A plus or minus is equal to 1 over square root 2m h bar omega square root. We have minus or plus h bar d dx plus m omega x. Now the commutator a minus a plus commutator, so this is written in square brackets, a minus a plus commutator applied to a function f is by definition a minus operator applied to a plus operator applied to f minus a plus operator applied to a minus operator applied to f. So we have to find these two terms. A minus operator applied to a plus operator applied to f. So that means we're applying 1 over square root 2m h bar omega. A minus operator has a plus for this term and a plus operator has minus for this term, but they both have this one, so we're getting the square of this term. So we will have 1 over 2m h bar omega. Now for the a minus operator we have plus h bar d dx plus m omega x. This will be applied to minus h bar. Now I'm applying this a plus operator to the function f, df dx plus m wx times f. So here I have applied the a plus operator where I had the square root term here, but from the second application of a minus, I will have the same one. So this is squared. So I get rid of the square root. And for a minus, I have plus. For a plus, I have for the minus term here. And this is applied to f, gives me this result. Now I'm going to apply this operator on the second term. Okay, so this will be equal to 1 over 2m h bar omega. All right. So what's the first term here? H bar d dx applied to minus h bar df dx. So we will get minus h bar squared. Second derivative of the function f with respect to x. And then we go to the next term. H bar d dx applied to mwxf. The first term, the derivative will be applied to x, so we will get mwf times h bar. So we have plus h bar mwf. And from the product rule, the d dx applied to the other term will be mwx df dx. So we will have plus h bar mwx df dx. And then we have nwx multiplied with this term. So this will give us minus h bar mwx df dx. And then we have the last term, m squared w squared x squared f. So plus m squared w squared x squared f. So this is what we obtain. Now, looking at this carefully, I realized that this term is equal to this term with a minus sign, so they will cancel out. So I will be left with the following. 1 over 2m h bar omega. I have, so let's write the last term first. M squared omega squared x squared times f, and then I also have h bar m omega times f. So plus m h bar omega in parentheses times f, and then the first term minus h bar squared, second derivative of the function f with respect to x. Okay, now for the other term in the commutator, which is a plus a minus applied to f, what we will do is we will replace, because the only difference between them is the sign of h bar, plus h bar with minus h bar inside the parentheses. That's the only difference between these two operators. Okay, so with that, I will have a plus a minus applied to f is equal to 1 over 2m h bar omega. I will have m squared w squared x squared, the same thing here. Now this h bar has changed sign, so this is minus m h bar omega times f. And This h bar changes sign, but it's squared, so that doesn't affect this term. Minus h bar squared d squared f dx squared. So you can see that I have evaluated both this term, and I'm going to subtract this from that. So if I do that, I will obtain a minus a plus commutator applied to the function f is giving me so if I subtract this term from this term, you can see that the first terms will cancel out. And then here I will have minus mh bar omega f divided by 2mh bar omega f. With the minus sign, this is going to become plus because I'm subtracting it. So I will have f over 2 here basically added to this f over 2, and these two terms are identical, so they will cancel out. So I will have f over 2 plus f over 2, which is equal to f. Okay, so what's the conclusion? Then this commutator, a minus a plus commutator, is equal to 1. It has no effect on the function. Okay. Now what were we supposed to do in part B? Compute a plus a minus phi in terms of phi and phi double prime, where phi of x is a function, wave function of x, and the derivative with respect to f of x times psi is psi plus x times psi prime. Okay, now I can rewrite my result from part A. From part A, I have the following result: a plus a minus applied to this function f is equal to 1 over 2m h bar omega. Then I have the square brackets m square omega square x square minus m h bar omega times f is equal to minus h, let's see, minus h bar square, second derivative of f with respect to x. So I have this result from part A. You can see that result here. Okay. Now what I'm doing here is I'm applying a plus a minus operators in this order to f, and now f is going to be replaced with the wave function psi. So the answer will be the following: a plus a minus applied to psi is so if I replace this function f with psi here, so you will get m square omega square x square times psi divided by 2mh bar omega, and then we will have minus mh bar omega multiplied with psi, and then we will have minus h bar square d square psi dx square. So this is going to be equal to 1 over h bar omega, and I take the 2m inside. You can see for this term 1 over h bar omega, 2m goes inside, minus h bar squared over 2m minus h bar squared over 2m psi double prime, second derivative with respect to x. And for the m squared w squared x squared term here, if I divide it by 2m, I will get mw squared x squared over 2. So this is mw squared x squared over 2 multiplied by psi. All right. And this is mh bar omega divided by 2mh bar omega. So that's minus f over 2, which is minus psi divided by 2. So this is our final answer for part B. And let's move on to part C. The Schrödinger equation above may be written as H applied to psi is energy times psi, where H is a differential operator, Hamiltonian operator. Use your previous results to write H in terms of A plus and A minus. Okay, well, this obviously looks like the Schrödinger's equation here. So you can see here A plus A minus applied to psi gives me 1 over h bar omega, and what I have in this parenthesis here is the Hamiltonian operator multiplied by 1 over h bar omega minus 1 over 2 applied to psi. So we can write the Hamiltonian operator as let's see here. A plus A minus plus 1/2 times h bar omega. So this is going to be A plus A minus plus 1/2 times h bar omega. So we were able to write the Hamiltonian operator in terms of the A plus and A minus operators, making this observation in part B that A plus A minus applied to the wave function is nothing but 1 over h bar omega Hamiltonian operator minus psi over 2. So 1 over h bar omega Hamiltonian operator minus product by 1/2 operator applied to psi gives us A plus A minus psi. So A plus A minus is 1 over h bar omega h operator minus 1/2. So we can write the Hamiltonian operator this way. And in part A, we calculated A minus A plus commutator by applying A plus operator first on the function, then A minus A minus operator first, then A plus. With the given definition, being careful with the sign of the h bar here. And when we obtain the result for A plus, A minus, A plus, our observation is that the only thing is the h bar changes sign for A plus, A minus times applied to f. So we can write easily the result for A plus A minus applied to f, and we have found that the commutator gives us 1. So we have used that result from part A to write A plus A minus applied to a one-dimensional wave function psi, time-independent wave function psi, and then we have noticed that the Hamiltonian operator can be written in terms of A plus and A minus this way.